In our previous lesson, we were taking a look at the equation of a straight line in R2, and we started with the standard slope-intercept form of an equation for a straight line, y equals mx plus b, and I related that to a new form, which is a vector equation of a line, and it makes use of the idea of slope, and we actually even give it the same symbol quite often, and that's a direction vector. So if you need to, you can review that, take a look at the previous lesson. The important thing to keep in mind between slope and direction vector is that they both make use of delta x and delta y. You just have to make sure you get the ordering straight. Another form of an equation that you're likely familiar with, although you probably haven't made use of it as much as you have of the slope-intercept form, and that's known as the Cartesian equation. And the Cartesian equation is in this form: ax plus by plus c equal to 0. So everything is on one side and it's set equal to 0. The correct form for the Cartesian equation is also that all of these values are integers. And sometimes you might even go so far as to have your integers such that a is also a positive integer. I'm going to require this first condition. The second condition, I think, is a nice too. It's like when we group equations. It's nicer to group equations so that we end up with positive rather than negative coefficients. So first of all, let's just start off with a couple of points, 5, 2 and 2, negative 2, 1, and let's come up with these three different equations and let's see how they relate to each other. Relating these first two to each other is what I did in the previous lesson, so I'm not going to spend a great deal of time on that, but I'm still going to go through all of the steps. So for part A, I want to express this in slope-intercept form. That's in the form y equals mx plus b. For part B, I want to represent it in vector form, so that's my position vector is equal to my initial position vector plus some coefficient times the direction vector. And my Cartesian form is going to be in the form ax plus by plus c equal to 0. So as far as slope-intercept form, the first thing I need is my slope, which is my change in y over my change in x. So I'm just going to use these in the order they're provided. So I'm going to call that x1, y1, x2, y2. So my delta y is going to be y2 minus y1. So that's going to be 1 minus 2 over x2 minus x1, which is negative 2 minus 5. And from that, we actually end up with negative 1 over negative 7, or 1 over 7. From here, I can now write my equation y is equal to 1 over 7x plus b, and then I just need to sub a point into that. Either of these points will do. I'll just use the first one. My y coordinate is 2, 1/7 times my x coordinate, which is 5, plus b. You can see this is going to end up being kind of an awkward number, it's going to be a fraction. So I'm going to give a denominator of 7 to both sides. So this becomes 14 over 7. This is 5 over 7, which is going to go to the other side, so that's going to become minus 5 over 7. And so my intercept turns out to be 9 over 7. And so we end up with our final form of the equation is 1/7 x plus 9 over 7. And nothing groundbreaking there. That's something you've been doing since, well, grade 10 at the latest is when you would have been looking at that. So now that we've done that, and we're going to move on to our vector form. So for this one, we need our direction vector. Our direction vector is very much like our slope, except for we write it in the form delta x, delta y. In the same way that we would write components xy, this is delta x, delta y. And so in this case, my delta x, I've actually got it written here. So there's my delta x, and up here there's my delta y, or you could just read it straight from your slope if you wanted to, because this is delta y over delta x. And so we can just go ahead and go straight to our simplified version since we have it in front of us here. So our delta x is equal to 7. Let's try that one more time. There we go. Our delta x is 7 and our delta y is 1 in its simplified form. Notice that we could have actually written this as -7, -1, because this is the opposite vector. And that's perfectly fine as far as direction goes. In describing the line, it doesn't matter whether we're going up the line or down the line, it's all part of the same line. And so now I'm going to write this as my position, my initial position vector plus some coefficient times my direction vector. My initial position vector is going to be one of the two, it's going to be the vector that points to one of these 2 points. So 5, 2, or -2, 1. And it doesn't actually matter which, it will still be a valid equation. So I'm going to choose the first one, 5, 2 plus t multiplied by the direction vector 7, 1. And we really do need to make a note that t is a member of the reals. Now, for the Cartesian, there's nothing you really need to do other than convert the slope-intercept form into Cartesian form. Now I'm going to show you something shortly to make another connection there. But for now, I'm just going to go ahead and I'm going to start with y equals 1/7 x plus 9 over 7. Keeping in mind what I said before about the fact that you want all of your coefficients to be integers, one of the things I'm going to do here is I'm just going to get rid of all fractions immediately, and I'm going to do that by multiplying through by 7. So I get 7y, and when I multiply this term by 7, I just end up with x, and when I multiply this term by 7, I end up with plus 9. And in keeping with the idea of my x coefficient being the one that I like to keep positive, I'm actually going to move my y to the right side, and I end up with 0 equals x minus 7y plus 9. Or you could write this as x minus 7y plus 9 equals 0, because typically Cartesian form is written that way. So notice that we didn't actually bring anything to do with vectors into this initially. So you already have all the skills you need to come up with the Cartesian equation of a line in R2. Now here's another way to think of it, but let's bring in vectors. If we're in R2, so we've got this line which I've got in blue. Any line which is perpendicular to this line is called a normal vector, or any vector which is perpendicular. And as you can see, there is a wide array of normal vectors. And in the previous lesson, I touched upon this as well. So these are normal vectors, or quite often they'll just be referred to as normals to the line. It turns out that if you have a line described in Cartesian form, one possible normal, that's why I say a normal to the line, not the only, but a normal to the line, is going to have a direction vector that matches a comma b. A is the coefficient of the x, b is the coefficient of the y. If you are interested in the normal unit vector, then we have this notation, which is the carré character, or sometimes called the hat. And so this means that this has a magnitude. So the magnitude of n hat is equal to 1. That is a unit vector. And the way that we get a unit vector is something we discussed before. We start with the original vector and we divide by the magnitude of that vector. And that gives us the unit vector. Sometimes it will be convenient just to leave it in this form, a comma b, just any old normal. Or you might be asked for a unit vector, so you can do this conversion. So find the Cartesian equation of the line passing through. So I've given you something, I've given you another one. And so we could, of course, go to the same method that we've done before, which is find the Cartesian equation of the line passing through this. So we will start with the slope, which is the change in y over the change in x. This is just standard algebraic methods. So it's 9 minus 5 over 2 minus 7. So we end up with 4 over negative 5, which we would normally write as negative 4 over 5. Now from here, you could go directly to the rest of the equation, the rest of the Cartesian, or not the Cartesian, the slope-intercept equation, but I'm actually not going to do that. Instead, I'm going to use the fact that the slope of negative 4 over 5, well, that tells me that I have a direction vector. And my direction vector is in the form delta x comma delta y. So my change in x in this case is 5, and my change in y is negative 4, because this is delta y over delta x. That's going to be an easy mistake for people to make, so please try to be careful about that. Now that I know my direction vector, I can also find my normal vector. Actually, I could have gone straight to my normal vector. Let me actually show you. Let me show you that. Because if this is my slope, then what is the slope of the perpendicular line to this? The perpendicular is going to be 5 over 4. And so my normal is actually going to be the delta x from the perpendicular and the delta y from the perpendicular. In other words, the normal direction vector is perpendicular to the original direction vector. So in this case, that turns out to be my delta x is 4 and my delta y is 5. And notice that compared to the direction vector, I have swapped the positions. That's like taking the reciprocal, and I had one positive and one negative, and so now I have two positives. So the overall effect is there's been one negative has been introduced here. That's a tough one to keep track of. It's probably easier as you're starting to go to the perpendicular slope. And now that I've done this, now that I've got this written, I want to remind you that the normal vector is in the form AB. So that means that this is the A value and this is the B value. They're already in integer form. So now I know my equation is 4x plus, not plus by, 4x plus 5y plus c is equal to 0. And as I did before, I can sub any point. And I'm not going to get picky about it. I'm just going to sub 7, 5. So I get 4 times 7 plus 5 times 5 plus c equals 0. And so I end up with 28 plus 25 plus c is equal to 0. And I end up with c is equal to negative 53. And it wouldn't have mattered whether I used either point there. So therefore my Cartesian equation is 4x plus 5y minus 53 is equal to 0. Now you might ask, and it would be a valid question to ask, why on earth would I worry about all of this vector nonsense when with the slope to slope-intercept form I can very easily find the Cartesian equation? And the answer to that is I'm showing this to you in the context of an example that you could do that way and you would understand it completely. I'm trying to get you to see and to appreciate this other way of doing it, because as we move through the course, the idea of using this normal vector, the idea of the Cartesian equation that you come to from a normal vector, once we move into R3, for example, the slope-intercept form won't be valid anymore. But we will still be able to have a normal vector, and we will still be able to have a Cartesian equation. So we are going to extend past the point where you can use the technique of just slope. So once again, I'm asking for the Cartesian equation. This time, I've got a line that is defined by parametric equations. And this was something I covered in the last lesson. Parametric equations come from the vector equation. So in parametric form, what this tells me is this is the initial position in the y, and the constant here is the initial position, in the x, and this is the initial position in the y. And then this one gives me my direction vector in the x, and this one gives me my direction vector in the y. So if I were to write this in the form r equals r naught plus t times the direction vector, I would end up with r equals, and let's rather than write that as r, let's write that as xy, so that's a general position vector, is equal to my initial x position, which is 1, and my initial y position, which is -4, plus t times my direction vector. My x direction component is -2, and my y direction component is equal to 3. So now that I've done that, from here, and I could have taken a shorter route to get here, but that is my direction vector, which is -2, 3. And so that tells me that my normal vector is equal to, I reverse them, and because I've got a single negative here, I'm going to change that into a positive. The other thing I could have done is I could have reversed them. So let's say, or I could have also said my normal vector was, I could have reversed them, 3, -2, and I could have introduced a second negative. So I went from 1 negative to no negatives. I went from 1 negative to 2 negatives. The net result is the same. Now that I have my normal vector, I can write my equation. So my equation becomes, let's see, it's going to be, this is in the form AB, so this is going to be 3x plus 2y plus c is equal to 0. And as we did before, I'm going to have to sub a point. This initial position vector is the same as the vector from the origin to an initial point, and so that means the point P naught is 1, -4. So I'm going to sub P naught into my equation and solve for C. 3 times 1 plus 2 times -4 plus C is equal to 0. So 3 minus 8 plus C is equal to 0. So that's -5, and so C ends up being +5. And so my equation in Cartesian form is 3x plus 2y plus 5 equals 0. Now, let's talk a little bit about the vectors again. What if we were asked about the angles where two lines cross? Now remember, when you're asked about an angle, you will, when you're talking about two lines crossing, unless they're crossed at 90 degrees, you're going to either find the obtuse or the acute. The way I've drawn it here, I actually have the obtuse angle up here and the acute angle there. But it's easy enough to switch between the two because you know that they have a supplementary relationship. The first angle adds up with the second angle to be 180. Now, if the equations were in vector or parametric form, what information do I have for these lines? If we are in vector or parametric form, then I have direction vectors. So I know the direction vectors for the lines. That would be M1 and M2. I'd be able to read those from the equations. So we would have something like this. I would have one direction vector for line 1, one direction vector for line 2, and I could find the angle theta between, and if I needed to, I could find 180 minus theta for the other angle at which they meet. And the way I would do that is if I have these vectors, then I can take the dot product using components, using the definition of dot product, but I can also find the magnitude of m1, the magnitude of m2, and then I can use this to find the angle theta. Slightly different situation if we have Cartesian form. If I have Cartesian form, then the information I have is actually for normal vectors. And I just want to point this out to you. This normal vector, I just want to show you, that normal vector is the same as that normal vector. It's perpendicular to this line L1. And this normal vector is perpendicular to this line L2. And so if we are trying to find the angle between them, well, that's the same problem that we were looking at before. This time I'm going to call it, I think, beta on the next slide. So if we're trying to find this angle in between them and we have these vectors, then we can use that same relationship we did before. But the hard part here is, how does this angle relate to, for example, here? And what you need to make use of is, if this is 90 degrees on this side, that actually is also, of course, 90 degrees on this side. Let's get this out of the way for now. So if this is beta, then this angle here is going to be 90 degrees minus beta. And now that we've got that angle, let's take that one out and put this one back in. And so this one, which I'll do with a triple, is going to be 90 degrees minus the angle from here, which is 90 degrees minus beta. And if you work through that, 90 minus 90 is 0, and the negative of negative beta is just beta. So the angle between these normals can be related down to here. And so we end up with this result if we use our dot product definition for the normal vectors, which we would use if our equations were in Cartesian form. Thinking ahead, looking ahead to R3. Right now we're in R2, but once we get into R3, this will continue to work. So just to recap, and I want you to capture this in your notes, the angle formed by two lines can be found using the dot product of either the direction vectors, so the direction vectors, that's going to be m1, m2, or the normal vectors, n1, n2. And in either case, we can use those vectors to find the angle between. And that's it for this lesson. I feel like mathematically or algebraically there was nothing difficult in that lesson, but conceptually, because we are changing the way that you have looked at things in the past, we're taking something you're familiar with and we're asking you to look at it in a different way, and I know that can be confusing. So this is one of those ones where it's not challenging algebraically, but there is a conceptual challenge that you are going to have to struggle with. Do the work with vectors as much as you can. Don't fall back onto those old habits, onto those comfortable habits.